Hey everybody, Thrasher here. This is K.1 on Graphing Motion. You might notice that in this video there is, well, me in the video. That's because I'm just going back and updating some of my older videos. So as you're watching these, some might have me in them, some might just have my voice, whatever. Eventually, theoretically, I'll get through updating all of them and they'll all have me in there. I don't know if it makes it better, but that's technology for you. We are in this video getting into graphing motion, looking at the main things that we've already learned about: position, velocity, and acceleration, but looking at how these kind of appear and how we interpret them in a graph. That's our goal for today. Okay, now, first of all, there are some things that you should hopefully already know when it comes to graphing motion, as I move my head a little bit out of the way. First, hopefully you know all these terms already: position, distance, displacement, etc., etc. If you don't know some of these terms, you should stop this video and go back and watch one of the prior videos on intro to motion. Maybe also make sure you remember that, like, the way we symbolized displacement was with that delta x, because you're going to see that symbol a lot. Okay, remember velocity is usually v, acceleration is a. You should know what these are to a decent degree, and you should know hopefully some basics about graphs. All right, there's slopes of a line for straight lines, y equals mx plus b, this kind of formula that you probably learned in algebra. Okay, what this m represents, that's the slope of a line. Slope, if you remember, is the rise divided by the run, or sometimes in math, maybe that was written as like y2 minus y1 divided by x2 minus x1. It's the change in the y-axis divided by the change in the x-axis, change in y divided by the change in x. That's what I have, bam, right here. Okay, that's going to be important as we go on. Okay, so let's get into some basics with graphing motion. And I'm going to start with a position versus time graph. So notice there's no numbers here, all right, but it has position, like where an object is located, on the y-axis, and time on the x-axis. We are pretty much always going to have time on the x-axis because it's easy to read. It's intuitive. It's letting us know that as time progresses, where is, in this case, an object located. So it looks like it starts at rest at 0 meters, it moves away, and then other things are happening as the graph progresses. But here is what I want to look at: the slope of this line, or of these lines. Obviously there's a few different lines, but what does the slope of this graph represent? It turns out it represents something very important. To figure out what it represents, let's remember the basic idea of slope. It's the change in y divided by the change in x. The change in the y value divided by the change in the x values. So let's just apply this equation for this graph. That's what I want to do. I want to apply this equation for this graph. So how would I do this? Okay, first for slope, it's the change in the y-axis. The change in the y-axis, that's position, right? So I'd be looking at the change in position, x2 minus x1. I know it's maybe a little funny that, there's the x-axis and I'm calling this what's on the y-axis x, because x is position, or it's going to be displacement as we're looking at the change. So if I'm looking at the change in the y-axis, that's the change in position. The change in position, that's what I have right here, divided by the change in the x-axis. What's the change in the x-axis? It's the change in time, t2 minus t1. So that means the slope of this graph, when I look at the slope of this line, or the slope of this line, or the slope of this line, I'm looking at the change in position divided by the change in time. Is that anything? Is that anything that we learned, the change in position divided by the change in time? Well, gang, that's velocity. That's why I'm looking at the slope here, because, oh my gosh, there is something very interesting and not necessarily intuitive about this graph. The slope of a position versus time graph gives us the average velocity. So look right here, look at this slope. This slope is positive, right? Up and to the right, that's a positive slope for math class. That means it has a positive velocity. The slope here, it's a straight line. The slope is constant. The velocity is constant. This is the key idea, one of the biggest ideas for graphing motion. The slope of a position graph or a position line on a graph gives you the object's velocity. Heck, you could calculate it. We could also describe it. So the slope of position gives you velocity. Let's do the same thing much faster, I think we can get away with a velocity versus time graph. So velocity is on the y-axis, time is on the x-axis. What does the slope equal in this case? Well, the slope is always the change in y. What's my y-axis? It's the change in velocity, v2 minus v1. Or, sometimes we'll write that as delta v. So now if I look at the slope of, say, this line, I would want to do the change in the y-axis, that's the change in velocity for this graph, divided by the change in the x-axis, that's time, t2 minus t1, or we write that as delta t. Whether I'm doing it for this line or this line, it's the same approach. I look at the change in the velocity, the change in y-axis, divided by the change in time, the change in the x-axis. What is this? Is this anything that we learned? Oh my gosh, that's acceleration. So these graphs are actually really valuable. Not only can you just read the y-axis, right, and figure out the velocity at one point, the time in one point, but you could actually figure out the acceleration of an object by looking at the slope of an object. So I have here, I'm going to delete this just like I did in the last graph. Again, the key idea, the slope of a velocity versus time graph, that gives us acceleration. So let's do some quick examples. That's my goal. Okay, here I have a position versus time graph. Sometimes they're labeled position. Sometimes they'll just have that label X written down there. Okay, but let's try and describe the velocity. Even though this is a position graph, let's try and describe the velocity at these 3 different times. So at A, what can you tell me about the velocity of this object based on this position versus time graph? Well, it looks like the velocity at location A, notice it's a straight line here, right? This is a straight line. My pen stroke isn't, but letter A is. So if the slope is constant, right? I'm looking at the slope. If the slope is constant, the velocity must be constant because the slope gives you the velocity. Is it positive, negative, or is the slope 0? The slope in this situation is positive, right? Up and to the right, that's a positive slope. That means the velocity is positive. This object, I don't know if it's a car, somebody walking, whatever, but at this location at A, they're moving at some constant and positive velocity. And yeah, we could calculate it. That's actually almost the easiest part of this whole thing. I'm not even going to do it in this example. I could calculate the velocity by looking at the change in the y-axis divided by the change in the x-axis. Okay, I'm not even going to do that here because that's usually pretty straightforward. You're just reading, if it has numbers on it, of course, you're reading the values and doing a quick calculation, rise divided by run. How about B? What's the velocity doing at location B? Can you answer this on your own? Well, the slope, because remember, I'm looking at slope, is 0, and it's also constant. That means the velocity is 0 and constant because the slope of a position graph gives us velocity. And finally at C, what's it doing? The velocity, again, I'm looking at the slope. The velocity is constant. And I say constant for all 3 of these because the line is straight. I don't have like a curving line. I don't see that anywhere in the graph. So it's constant. It's staying the same all throughout this section C. And here, the slope is negative down and to the right. So the velocity is constant and negative. Okay, let's look at another couple of examples. Now it's a velocity versus time graph. So for number 2, can you describe now the acceleration? If it's a velocity graph, again, the slope tells us now, because it's a velocity graph, it tells us the acceleration. So what's the acceleration in this scenario? Is it constant or is it changing? It's constant because the slope is constant. Is the acceleration positive, negative, or 0? The acceleration is positive. Can you tell me, is this object speeding up or slowing down? Ooh, it turns out this object in this graph is speeding up. I'll talk more about that in a second. Let's look at 3. Okay, the acceleration. Now, is the acceleration constant or is it changing? Remember, you're looking at the slope. The acceleration is constant because the slope is constant. I still have a straight line. Is the acceleration positive or negative? The acceleration is positive. Oh, did I get you? Did you say it was negative? I'm looking at the slope. For acceleration, if I'm given a velocity graph, I care about the slope. The values of velocity are negative in this graph, but that's not what I'm looking at. The acceleration is the slope of the line. The slope of the line is still positive. Any line up and to the right, no matter where it is on the graph, any quadrant, it's still positive. So the acceleration is positive. Last question, the toughest one on the slide. Is this object right here, is it speeding up or slowing down? This object is slowing down. Slowing down. And to be honest, you could have gotten that in a couple different ways. If you look at the velocity, notice the velocity starts here and then it's getting closer and closer to zero. So if I have some negative 500 meter per second or mile per hour velocity, but I'm approaching zero, I'm slowing down. But also remember what we learned from the other class, okay? If you have a negative velocity and a positive acceleration, if the two are opposites, well, that's when you're slowing down, okay? So because the values of the velocity are negative, but the value of the slope, the acceleration, is positive, those are opposites, that always means the thing is slowing down. Tricky, 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 but you'll get practice. Okay, I really just have one more main slide and then kind of a cheat sheet, and we're almost done. Okay, the toughest part about graphing motion is not in giving a graph and then interpreting it. It's drawing other graphs from one that is given. What I mean by this is, here I have a velocity versus time graph. Okay, I want you to draw, and we'll do it together actually. I want you to draw the acceleration versus time graph, and then we'll do it later, the position versus time graph. Okay, and I'll have to move my screen. If the velocity versus time graph looks like this, okay, you can draw the acceleration, remembering, what do I look for acceleration? It's the slope. The slope of a velocity versus time graph gives me acceleration. So let's look at the slope of this graph. Is the slope constant or is it changing? The slope is constant. Okay, straight line, constant slope. Is the slope positive, negative, or zero? It is positive. So the slope of this velocity graph is constant, it's a straight line, and it's positive. That means the acceleration should be constant and positive. How do I draw a constant and positive acceleration? Well, forgive me, my drawing abilities on this computer might not be great, but it should be a constant acceleration. Now I'm looking at just the y value, right? The acceleration is now the y value of this graph. The acceleration should be constant and positive above, the x-axis, above the origin. Okay, so here I have a constant and positive acceleration. Last thing we're doing, we're almost done with this video. It's a little tougher, okay? Could you draw the acceleration of this object, given, again, that velocity graph? I'm actually going to cover myself. I'm going to cover that acceleration. Don't look at the acceleration graph for this. Maybe I'll move it right down there. But we're still going to focus on this velocity graph, okay? Now, the slope of the position graph is the velocity. So now, oh my gosh, okay, I kind of want to go the other way. Here, the value of the slope, of the velocity is getting more and more and more. If I'm looking at a position graph, it's the slope of position gives the value of velocity. So normally, before I was looking at the position graph, I was looking at the slope, and then I was getting the velocity. But now I want to go the other way. If I can figure out the value, the y value of the velocity graph, that gives me the slope, of the position. These are going to be tough, and I don't think you're going to get it right away after this video, and that's okay. We'll be doing practice. Okay, but what I mean by this is, now to get position, the position is the slope of the velocity graph. The velocity is getting greater and greater and greater, right? Let's just focus on this graph. The speed of this car, the velocity of the car over time is getting more and more. It's maybe, 1 meter per second, then 2 meters per second, then 3 meters per second. The position graph, we know the velocity by the slope. So if the velocity is getting bigger, the slope of a position graph should be getting bigger. So the slope of this graph, or how this graph should actually look, is going to be a curve, something like this. It's just a sketch. It's not exact. I don't know exactly what it is. There's no numbers. But here is the sketch. Again, how did I get this? The velocity of this object is getting bigger and bigger and bigger over time. 1, then 2, then 3. You know, it's getting bigger, whatever the numbers are. Okay? Well, in a position graph, the slope tells me the velocity. So if the slope is getting bigger, steeper and steeper, that's what the velocity is doing. And that matches what I have. These are the toughest. Oh my gosh, going backwards. It's kind of easy to go from position to velocity to acceleration. Those are at least easier. All right? It's tougher to go the other way. Again, super tough. We'll get more practice in the next couple of classes. Okay? So the last thing I'm going to show you, I got to move my head one more time. Okay, I would recommend you hit pause in this video and write these down in your notes. Okay, this is the toughest part about doing these graphs, doing these sketches. And these 3 slides are kind of some cheats, some tips to help you with these graphs. So I recommend you hit pause, you write this down in your notes. I hope you were kind of maybe writing down everything, but if you weren't writing down anything else, write this down. We're going to be doing practice in class, okay, and with your teacher if you don't have Mr. Thrasher. But write these down. It's going to help you when we do this practice in class. But that's the end of my video. Thanks a lot for watching. I'll see you next time.